The universe sprawls across infinity, an expanse of stars, galaxies, and empty space stretching beyond the limits of our comprehension. Each time we gaze into the night sky, we are not merely looking at distant stars but peering into the past, billions of years of cosmic history frozen in light. Yet, as we peer into that vastness, one question gnaws at us. If the universe is expanding, what is it expanding into? This question is not just a curiosity, it is a profound puzzle that challenges the very nature of existence itself. To imagine the universe expanding into something means we must first try to understand what that something could be. Could it be a limitless void, an endless emptiness that stretches beyond time and space, or could there be something else, something beyond our current understanding? The vastness of space seems to stretch into an abyss, but it's more than just the size that leaves us stumped. It's the very fabric of reality itself, the rules that govern our universe, that could be different at this grand scale. For centuries we have looked out into the cosmos with awe and wonder, but as our tools have grown sharper, the questions we ask have grown deeper, more unsettling. The truth is, we have only scratched the surface of understanding. This is not just about what is out there, but about what the universe itself actually is. It isn't just an empty void as it once might have seemed. It is a complex, dynamic system, constantly changing, expanding, and evolving. But the core mystery remains: what exactly is it expanding into? To tackle this, we first need to look at how we even know that the universe is expanding. In the 1920s, the astronomer Edwin Hubble made a breakthrough observation that would forever alter the way we understand the universe. By studying the light coming from distant galaxies, Hubble discovered something astonishing. The galaxies were moving away from us. More importantly, the farther a galaxy was, the faster it appeared to be receding. This was a key piece of evidence that suggested not only that the universe was expanding but that the expansion was happening everywhere, all at once, in every direction. At first glance, this revelation may seem strange. How can the universe expand into something? After all, space is, well, space, an infinite void. If the universe is expanding, we might naturally assume it's growing into this void, filling it up. But here's the catch: space itself is expanding. It's not as though galaxies are traveling through an pre-existing space. Instead, the space between galaxies is growing. This means the universe is not expanding into anything at all, at least not in the way we typically understand expansion. It is simply becoming larger, with more and more space being created between objects as time goes on. This notion challenges our fundamental understanding of space and time, and it's where things start to get really confusing. Our conventional understanding of the world, shaped by everyday experiences and grounded in physical laws, begins to falter when we move to the cosmic scale. How can something grow when there's no clear boundary, no edge, no place for it to expand into? Are we on the brink of an entirely new understanding of space and time, one that shatters everything we thought we knew? The answer, of course, is that we don't fully know. There are theories, yes, but none that can offer a definitive answer. Some physicists have suggested that the expansion of the universe might be happening within an infinite and unbounded space, a hyperspace, that exists outside our perception. This leads to the possibility that, far beyond the observable universe, there could be an infinite void, a cosmic nothing into which our universe expands. But if that's the case, what is this nothing? Is it truly nothing, or is it something we just don't have the tools to understand? Then there are theories suggesting that our universe is part of a much larger cosmic structure, something known as the multiverse. This idea proposes that our universe may not be unique at all, but rather one of many universes existing within a vast and potentially infinite multiverse. If this is the case, then perhaps our universe's expansion is merely one bubble in an ever-expanding cosmic foam, with other universes similarly expanding into their own unknowns. But again, this only deepens the mystery. If the universe is expanding into nothing, what does that even mean for the other universes? And what exactly is this nothing that we speak of? As these questions multiply, we begin to realize that the very idea of nothing is a slippery concept. The question of what the universe is expanding into touches on deep philosophical and scientific debates about the nature of existence. Is nothing truly a vacuum, an absence, or is it something more elusive, more intricate than we can currently imagine? In many ways, it seems that the more we explore the nature of space and time, the more the boundaries between what is real and what is imagined blur. What if the nothing outside our universe is just another form of existence, one that operates on laws entirely alien to us? The tension here is palpable. On one hand, we are in awe of the universe's complexity and beauty, but on the other, we are confronted with the unsettling idea that the answers to these questions may always be just out of our reach. Our understanding of the universe is limited not just by our technology, but by our minds themselves. We can look into the vastness of space, chart galaxies, measure distances, and track cosmic movements, but there is a haunting sense that, at the farthest reaches of space, there may always be something we can never understand. What is beyond the edge of the known universe? Will we ever know, or are we forever bound by the limits of our own perception? In the coming sections, we'll delve deeper into the history of our understanding of the universe, the theories that have emerged to explain its behavior, and the mind-boggling implications of what it might be expanding into. Along the way, we'll uncover not just answers but even more questions, puzzles that may never be solved in our lifetime, but that push the boundaries of human curiosity and wonder. This journey will not only take us through space, but also through the very nature of existence itself, as we grapple with the fundamental mysteries of our cosmos. And so, we are left with this question: if the universe is expanding, what is it expanding into? The answer may lie beyond our current understanding, but it is the pursuit of this very question, this relentless quest for knowledge, that propels us forward. Even if the answers remain elusive, it is the search itself that defines our place in this vast, mysterious cosmos. And with every discovery, we inch closer to understanding not just the universe, but the very nature of existence itself. To understand the true nature of the universe, we must begin at the very beginning, the birth of everything we know. In the beginning there was no space, no time, no matter, and no energy. Just a singularity, an infinitely dense point of pure potential, brimming with the possibility of everything that would follow. Then, in an event that defies imagination, the universe as we know it sprang into existence, bursting forth in a cataclysmic explosion that created not only all the matter we see around us but also the very fabric of reality itself. This event, known as the Big Bang, took place approximately 13.8 billion years ago. It wasn't an explosion in the traditional sense but more of an expansion, a rapid stretching of space itself. In the first moments of the Big Bang, the universe was an unimaginable soup of subatomic particles, all of them compressed into an incredibly small, hot, and dense space. It was a state where the usual laws of physics break down, where our understanding of time and space itself begins to dissolve. The universe didn't begin in a specific location. It began everywhere, all at once. There was no outside to the universe because the universe encompassed everything that existed, and there was no space or time in which it could expand. But this moment, this beginning, is far from simple. The conditions of the universe in those early moments were so extreme that even our most powerful scientific tools can hardly describe them. The temperatures were unimaginable, hotter than the cores of stars, hotter than any supernova. In those early moments, the universe was a seething, chaotic mass, and as it expanded, it cooled, allowing matter to form. Within just a fraction of a second, the universe underwent an event known as inflation, where space itself expanded at a mind-boggling rate. In less than a trillionth of a second, the universe grew from a point smaller than an atom to something far larger than our current observable universe. As the universe cooled, the simplest building blocks of matter began to emerge. Quarks and electrons formed, and in the blink of an eye, atoms began to come into being. The first light, the faint glow known as the cosmic microwave background radiation, was released, a snapshot of the universe as it was about 380,000 years after the Big Bang. This light, still detectable today, serves as one of the most important pieces of evidence for the Big Bang theory. It is a remnant of that moment of creation, a relic of the birth of the universe. The early universe was not just expanding in size but also in complexity. Within a few 100 million years, the first stars began to form, igniting the fusion processes that would eventually create heavier elements like carbon, oxygen, and iron. These stars would eventually explode as supernovae, scattering these elements across space and seeding the formation of planets, moons, and galaxies. It is through this process, this cosmic recycling of matter, that the very ingredients for life were created. These elements, created in the hearts of stars, would become the building blocks of everything that would follow, from the earth we live on to the very bodies we inhabit. In those first few moments of the universe's existence, a critical transition took place. The universe went from being a nearly homogeneous, featureless expanse to one where the forces of gravity began to pull matter together, forming the first galaxies. The birth of galaxies, clusters of stars, and nebulae marked the start of structure in the universe. Over billions of years, galaxies merged, stars were born and died, and black holes grew at the centers of galaxies. And yet, even as galaxies and stars formed, the universe was still expanding. an expansion that, as we now know, has never stopped. The expansion of the universe, initially thought to be a slow, steady process, was revealed to be accelerating. This discovery was one of the most surprising developments in modern cosmology. In the late 1990s, two independent teams of astronomers, using observations of distant supernovae, found that the universe's expansion was not slowing down as had been previously expected, but rather speeding up. The culprit behind this acceleration was an unknown force, which we now call dark energy. This discovery has had profound implications for our understanding of the universe's fate, suggesting that it will continue expanding at an ever-increasing rate, eventually leading to a distant, cold, dark future. Yet even with all this knowledge, we still don't know why the universe began as it did. What caused the Big Bang? Was it an accident of nature, or is there a deeper reason behind its birth? These questions remain unanswered, but the pursuit of the answers has driven humanity to the edges of our understanding. We have learned that the universe was once an almost incomprehensible singularity, but how it came to be, and why it came to be the way it is, remains a profound mystery. Theories abound. Some suggest that the Big Bang could be the latest in an infinite cycle of expansion and contraction, while others posit the existence of a multiverse, a vast ensemble of universes, each with its own Big Bang. Perhaps the most tantalizing possibility is that the Big Bang is not a one-time event, but rather the beginning of a series of cycles, a never-ending process of creation and destruction. In this view, the universe is born, lives, and dies only to be reborn in another Big Bang. Theories of cyclical universes suggest that the cosmos may not be a singular, finite entity but part of an eternal cycle, an infinite loop of creation and destruction. This idea challenges our perception of time itself, suggesting that the very flow of time might be cyclical rather than linear. But the question remains, if the universe began from nothing, what was there before the Big Bang? What was the origin of the singularity? Some scientists have suggested that the Big Bang may not have been the beginning of everything but rather the moment when our current universe emerged from a previous state of existence. Others propose that the Big Bang was the result of quantum fluctuations, tiny, unpredictable events at the subatomic level that sparked the creation of the universe. In this view, the birth of the universe might not have been an isolated event but part of a larger, quantum process that happens repeatedly across the cosmos. These questions don't have easy answers. In fact, they may be questions we cannot fully answer, not because we lack the intelligence or technology, but because the nature of the question itself may be beyond the reach of human understanding. The birth of the universe, the Big Bang, is so far removed from our daily experiences, so fundamentally different from anything we can observe, that it becomes almost impossible to truly comprehend. Yet, as we reach out into the farthest corners of the universe, we are also reaching inward, probing the deepest mysteries of existence itself. We are left with the haunting realization that the answers may never come. Perhaps we are simply not equipped to understand the true origins of the universe. Still, the search for these answers continues. With every discovery, we learn more about the universe's past, its present, and perhaps its future. Each piece of knowledge we uncover adds a new layer to our understanding of the cosmos, bringing us closer to the elusive truth. But in the end, it is the search itself, the pursuit of knowledge, that keeps the mystery alive and fuels our desire to explore the unknown. The universe, vast and unfathomable, remains a puzzle, one that may never be fully solved, but one that will always captivate the human imagination. As we continue to delve into the mysteries of the cosmos, one fact stands undeniable: the universe is expanding. This realization, which was once a revolutionary theory, has now become a cornerstone of modern cosmology. The notion that the very fabric of space itself is stretching, causing galaxies to move away from each other, fundamentally changes how we view the universe and our place within it. But what does this expansion really mean, and what are its implications for the future of the cosmos? The idea that the universe is expanding was first proposed by the Belgian priest and scientist Georges Lemaitre in the early 20th century, and later confirmed by the observations of American astronomer Edwin Hubble in 1929. Hubble, while studying the light emitted by distant galaxies, discovered that those galaxies were receding from us. More importantly, the farther a galaxy was, the faster it appeared to be moving away. This was a breakthrough moment for astronomy. It suggested that space itself was stretching, pulling galaxies apart. Hubble's observations were based on what is known as the redshift effect, where light from distant galaxies is stretched toward the red end of the spectrum as they move away from us, much like how the sound of a car's engine grows lower as it speeds away. The greater the redshift, the faster the galaxy is moving away. This discovery fundamentally changed our understanding of the universe. If galaxies are receding from each other, it means that at one point in the past, they must have all been closer together. This realization led to the theory that the universe had a beginning, an origin point from which everything emerged. The Big Bang theory, already gaining traction among scientists, found solid evidence in Hubble's work. The universe was not static as was once thought, but in a constant state of flux, expanding outward from an incredibly dense and hot state. But what does it mean for space itself to expand? To visualize this, it helps to think of the universe not as a collection of objects floating within a pre-existing space, but as a fabric, a stretchable, malleable medium in which objects exist. Imagine a rubber sheet being stretched with dots on its surface, representing galaxies. As the sheet stretches, the dots move further apart. Similarly, as space itself expands, the galaxies move away from each other. This analogy, though imperfect, provides a glimpse into the nature of cosmic expansion. Galaxies are not moving through space as objects travel across the surface of the Earth. Rather, space itself is stretching, and it is this stretching that causes galaxies to recede from one another. But here's where the mystery deepens. If the universe is expanding into something, what exactly is that something? As we discussed earlier, space itself is expanding, and so the idea of the universe expanding into an empty void doesn't seem to apply. This leads to a profound question. If space is expanding, then what happens at the very edge of the universe? What lies beyond the observable limits of the cosmos? The answer, or rather the lack of a clear answer, creates a tension that has driven scientists and philosophers alike to ask whether we are seeing the true shape of the universe or if our view is limited by our observational tools and concepts. One of the key factors in understanding the expansion of the universe is the concept of the cosmological horizon, the observable limit of the universe. The farthest distance we can observe is determined by the speed of light and the time it takes for light to travel across space. This means that there are regions of the universe that are so far away that their light has not yet had time to reach us, even though the universe has been expanding for billions of years. This cosmic horizon represents the boundary between what we can observe and what lies beyond our detection. What happens beyond this boundary? The expansion of the universe doesn't cease at the edge of the observable universe. Instead, space itself continues to stretch, and the galaxies beyond the cosmological horizon continue to recede from us. As the universe expands, it carries galaxies away from one another, and in some cases, these galaxies move away faster than the speed of light. This does not violate the laws of relativity, because it's not the galaxies themselves moving faster than light within space, but rather the space between them expanding. This phenomenon creates a strange reality. There are galaxies beyond our observation that are unreachable, moving so fast that no signal, not even light, can ever reach us from them. This expansion is not a uniform process. Some regions of the universe expand faster than others, depending on the distribution of matter and energy. The most significant factor driving this acceleration is the mysterious force known as dark energy, which was discovered in the late 1990s. Dark energy is a form of energy that seems to permeate all of space and is responsible for the accelerating expansion of the universe. Its discovery has profound implications for the future of the universe. If dark energy continues to dominate the expansion, it could eventually lead to a big rip, where the expansion of the universe accelerates so rapidly that it tears apart galaxies, stars, planets, and even atoms. This chilling possibility is one of the many ways the universe's expansion could ultimately end, and it underscores just how little we truly understand about the forces shaping the cosmos. On the other hand, if the expansion were to slow down and reverse, the universe could eventually experience a big crunch, where the gravitational pull of matter causes the universe to collapse in on itself. But the discovery of dark energy has made this scenario seem increasingly unlikely. Instead, the most probable future of the universe appears to be one where it continues to expand, driven by dark energy, growing colder and darker as galaxies recede from each other, stars burn out, and all matter is spread thinner and thinner across the vastness of space. This notion of an ever-expanding universe invites a more philosophical reflection. As we watch the galaxies move further apart, it can be easy to feel a sense of isolation, as though the universe is not only expanding in size but also in meaning, leaving us with ever-deepening questions. The universe, once thought to be a stable, closed system, is in fact a dynamic, evolving entity, constantly changing, always growing, and perpetually slipping beyond the horizon of our understanding. The more we learn, the more we realize how much there is still left to discover. Perhaps most unsettling of all is the realization that, in a sense, we are witnessing a universe that is both ancient and future at the same time. The light we see from distant galaxies takes millions or even billions of years to reach us, meaning we are looking into the past. Yet, at the same time, the expansion we observe is a future event unfolding before our eyes. The universe is a story written in the language of light and time, and our place in it is both temporary and eternal. The further we peer into the cosmos, the more questions arise, each answer opening the door to new mysteries. This sense of perpetual motion, the expansion of the universe itself, underscores the mystery at the heart of the cosmic narrative. It invites us to consider the nature of space, time, and reality itself. What is the true nature of the forces that drive this expansion? What lies beyond the observable universe, and how do we reconcile the vastness of space with our small place within it? These questions are not easily answered, but they remind us that the universe is far from a static, predictable entity. It is an ever-changing, ever-growing mystery, one that will continue to unfold long after our understanding reaches its limits. As we move forward, exploring the future of the expanding universe and its ultimate fate, the mystery of what the universe is expanding into remains one of the most profound puzzles of modern science. In the end, it is not just the answers that matter but the questions themselves, the questions that continue to push us to look beyond the stars and into the very heart of existence. As we stand at the edge of understanding, contemplating the vastness of the cosmos, one of the most fundamental questions we encounter is not just about the universe's expansion but about its very shape. What is the true structure of the universe? For centuries, astronomers and physicists have grappled with this question, seeking to understand whether the universe is flat, spherical, or even shaped in a way that defies our conventional understanding of geometry. The shape of the universe may seem like a purely academic question, but its answer holds profound implications for our understanding of space, time, and the very nature of reality itself. The earliest models of the universe imagined it as a simple, static entity, perhaps a vast sphere or a collection of stars arranged in a regular pattern. These ideas were rooted in ancient philosophies and religious beliefs, with the Earth placed at the center of the universe. Over time, as our understanding of the cosmos evolved, the idea of a static, Earth-centered universe gave way to the notion of a dynamic, ever-expanding one. The shift from a geocentric to a heliocentric model, as proposed by Copernicus and later confirmed by Galileo and Kepler, marked a dramatic transformation in our understanding of the universe's structure. Yet even with these breakthroughs, the true shape of the universe remained elusive. The breakthrough came with the development of general relativity by Albert Einstein in the early 20th century. General relativity introduced a radical new idea, that space itself is not a static, unchanging stage on which objects move but a dynamic entity that can be curved, warped, and stretched by the presence of mass and energy. In this view, the universe is not simply a three-dimensional space in which objects move, but a four-dimensional fabric, spacetime, interwoven and shaped by the gravitational influence of all matter and energy within it. The shape of this fabric, and thus the shape of the universe itself, became a central question in cosmology. The simplest model for the shape of the universe is that it is a sphere, with matter distributed evenly in all directions. This model is known as a closed universe, one that is finite in size and would eventually collapse in on itself under the influence of gravity. In this model, the universe has a clear center and an edge, and if you traveled far enough in one direction, you would eventually return to where you started. But this closed model has been largely ruled out by observations. The discovery that the universe is expanding, and that galaxies are moving away from one another, suggests that the universe does not have a central point or a boundary. It seems to be infinite, stretching outward in all directions, without any discernible edge or center. Yet even as the idea of a closed universe was abandoned, questions about the universe's true shape persisted. Some scientists proposed that the universe could be flat, without any curvature, like a giant, endless plane. In this model, the universe stretches infinitely in all directions with no boundaries or edges. The idea of a flat universe was supported by some early observations, but it wasn't until the 1990s that evidence began to accumulate in support of this theory. Measurements of the cosmic microwave background radiation, the faint glow left over from the Big Bang, revealed subtle patterns that suggested the universe is indeed flat, or very close to flat, on large scales. However, the story doesn't end with a flat universe. There are still alternative models to consider, including the possibility that the universe is curved in a higher dimensional space. This idea is rooted in the concept of a multidimensional spacetime, in which the three dimensions of space that we experience are part of a larger, more complex structure. In this view, the universe could be curved in ways that we can't directly observe, with higher dimensional space wrapping around us in ways that defy our intuition. This idea is supported by string theory, a framework in theoretical physics that suggests the existence of additional spatial dimensions beyond the familiar three. In this scenario, the universe may be shaped like a higher dimensional object, such as a hypersphere, that we can't directly perceive. As intriguing as these possibilities are, they raise even more fundamental questions about the nature of space itself. If the universe is curved, what does that curvature mean for the boundaries of space? Is there an outside to the universe, a place beyond the curvature where space ceases to exist? The very notion of curvature challenges our perception of space as a simple, empty void in which objects exist. Instead, space may be a dynamic, complex entity that operates on scales far beyond our everyday experience. This realization forces us to reconsider what it means for something to be outside the universe, or even whether such a concept is meaningful at all. One of the most mind-bending aspects of this question is the possibility that the universe might be infinite, with no beginning or end, no center or edge. In such a scenario, the universe would stretch endlessly in all directions, with galaxies continuing to recede from one another as space itself expands. This infinite universe would have no true shape in the way we understand it. It would be more like a never-ending process, constantly unfolding, constantly expanding. This idea aligns with certain models of the universe, such as the one proposed by the physicist Alan Guth in his theory of cosmic inflation. According to this theory, the universe underwent an exponential expansion in the first moments after the Big Bang, stretching from a microscopic point to a vast, nearly infinite expanse in a fraction of a second. Yet, even as we explore the possibility of an infinite universe, we are confronted with another mystery, the apparent flatness of the universe. If the universe is indeed infinite, why does it appear to be so uniform? On the largest scales, the distribution of galaxies, stars, and other cosmic structures is remarkably consistent, with only slight variations in density. This uniformity, known as the cosmological principle, suggests that the universe looks roughly the same in all directions, regardless of where you are. But how could this be the case if the universe is so vast and so old? Shouldn't there be more variations, more regions of dense and sparse matter? The answer to this question may lie in the process of cosmic inflation, which effectively smoothed out any initial irregularities in the early universe. The rapid expansion of space in the first moments after the Big Bang stretched any fluctuations in density to such an extent that the universe became almost perfectly uniform. These questions, about the curvature of space, the shape of the universe, and the mysteries of its vastness, reveal the deep complexity of the cosmos. They challenge our assumptions about the very nature of reality. If the universe is flat, or if it is curved in ways we can't directly perceive, what does that mean for our understanding of space and time? Are we seeing the universe as it truly is, or are we limited by our human perspective, bound by the constraints of our senses and instruments? And if the universe is infinite, what does that imply about the very notion of space itself? The true shape of the universe may remain elusive for some time, but the search for answers to these questions is one of the most profound scientific endeavors of our age. As we continue to refine our models, to gather more data, and to push the boundaries of our understanding, we are forced to confront the limitations of our own knowledge. The universe is far more complex and mysterious than we ever imagined. And as we peer into the depths of space, we are reminded that, just as we have no definitive answer about the shape of the universe, we may never fully grasp the true nature of the reality in which we live. The universe is both an endless puzzle and a breathtaking wonder, an ever-expanding mystery that continues to elude us, no matter how far we reach. As we continue our journey into the unknown, exploring the limits of our universe, we begin to encounter a boundary that is both physical and perceptual, the observable universe. It's a concept that might seem simple at first glance, but as we peer deeper into the cosmos, the nature of this boundary becomes more complex, more enigmatic. What lies beyond this observable limit? And what does the concept of observable even mean in the vastness of space? The observable universe refers to the region of space from which light has had enough time to reach us since the beginning of the universe. This distance, or rather this region, is determined by the speed of light and the age of the universe. Because light travels at a finite speed, the farther away an object is, the longer it takes for its light to reach us. This means that when we look into the night sky, we are not seeing things as they are right now but as they were in the past. The farther we look, the further back in time we are looking, and the more we understand that the universe has been constantly evolving. The observable universe is not a static boundary. It is a moving frontier that shifts outward as light from distant stars, galaxies, and other cosmic objects reaches us. The size of the observable universe is currently estimated to be about 93 billion light-years in diameter, But this is not the absolute size of the universe. It's just the portion of the universe that we can observe, based on the light that has had time to travel to Earth since the Big Bang. Beyond this limit, the universe continues, but it is beyond our current ability to see or measure. This brings us to a profound realization. The observable universe is not the entirety of the cosmos. There is, in theory, much more beyond it, regions of space and time that are simply too far for us to observe. If we consider the expansion of the universe, it becomes clear that the observable universe is only a tiny fraction of the whole. As space expands, more and more of the universe is moving beyond our observational reach. This fact raises a multitude of questions. What lies beyond our observation? How can we even begin to conceptualize what exists beyond the observable limits? One of the most fascinating aspects of this discussion is the realization that we may never be able to observe beyond this boundary. The universe is expanding, and galaxies that are currently within our observational range are moving away from us at an accelerating rate. Some of these galaxies are receding so quickly that their light will never be able to reach Earth, no matter how much time passes. This phenomenon is known as the cosmological horizon, and it creates a hard limit on our ability to observe the distant cosmos. While we can see objects millions or even billions of light years away, we are effectively blind to everything beyond a certain distance, as the light from those objects will never reach us. This accelerating expansion is driven by dark energy, an invisible force that permeates all of space and is responsible for pushing galaxies apart at increasing speeds. Dark energy's discovery in the late 1990s revolutionized our understanding of the universe, but it also introduced a profound mystery. What is dark energy and how does it work? Its presence means that the universe will continue to expand forever, and that parts of the universe will move beyond our ability to observe them. In the far future, as the expansion continues, galaxies that are currently visible to us will fade from view, lost in the growing distance between them and Earth. The concept of the observable universe becomes not just a scientific curiosity but an existential realization. The universe is expanding and we, as finite observers, will forever be limited in our view of it. The implications of this expanding universe reach beyond just our ability to observe. If parts of the universe are receding faster than the speed of light, does that mean they exist outside of space and time as we know it? The idea that distant galaxies are moving away faster than light challenges our understanding of the cosmic speed limit set by Einstein's theory of relativity. But the key here is that the galaxies are not moving through space at faster than light speeds. Rather, the space itself is expanding, stretching the distance between us and those galaxies. This distinction is subtle yet crucial. It means that even though objects can move away from us faster than light, they are not violating the laws of physics. Still, it forces us to confront the question of what it means to be observable. If a galaxy is moving faster than light, does it even make sense to say that it exists within our universe, or is it part of an entirely different cosmological region that we can never reach? This also introduces an uncomfortable truth. The universe, as vast as it is not only expanding but also becoming less accessible to us with each passing moment. While we can continue to observe objects within the observable universe, the portion of the cosmos that we can interact with is shrinking, not growing. The vast majority of the universe will forever remain out of reach, obscured by the relentless expansion of space. In a sense, the universe is becoming more and more distant, not just physically but existentially. This creates a paradox. The more we learn, the more we realize how little we can truly know. Yet, despite the vastness and the limitations, the observable universe is an incredible achievement in human understanding. Through powerful telescopes and innovative technologies, we have been able to peer deep into space, catching glimpses of the early universe and observing the formation of galaxies, stars, and planets. We have discovered exoplanets orbiting distant stars, some of which may even harbor life. We have mapped the distribution of galaxies and discovered that the universe is filled with a vast cosmic web of interconnected structures. But as we look deeper, we encounter the inevitable barrier, the edge of what can be seen. This brings us to a central paradox of modern cosmology. The universe is both immeasurably vast and incomprehensibly distant, yet it is intimately tied to the human experience. We are stardust, born from the remnants of ancient stars that lived and died long before the Earth was formed. The atoms in our bodies are forged in the hearts of stars, and our very existence is intricately connected to the unfolding of the universe. Our desire to understand the cosmos, to peer into the depths of space and time, is driven by a deep existential need to comprehend our place in this vast and mysterious expanse. But what if we can never truly know what lies beyond the observable universe? What if the edge of the universe is not a physical boundary but a conceptual one, an inherent limitation of human understanding. This does not diminish the importance of our cosmic exploration. Rather, it enhances the mystery. We are driven by curiosity, by the desire to learn and discover, but we must also acknowledge the limits of our knowledge. The universe, in its infinite vastness, reminds us that there are always unknowns, mysteries that may never be fully understood, even by the most advanced civilizations. In the coming years, our understanding of the observable universe will continue to evolve. New technologies such as the James Webb Space Telescope will push the boundaries of what we can observe, revealing the early universe in unprecedented detail. Yet, even as we advance, we will always face the realization that there is an entire universe beyond our reach, stretching out into infinity, beyond the grasp of light, beyond the horizon of observation. The universe is vast and we are just beginning to understand its scale. But no matter how much we discover, we must always remember that the true limits of the universe may be beyond our understanding, hidden in the vast, uncharted regions that lie beyond the observable cosmos. And perhaps, that in itself, is the greatest mystery of all. As we look up into the stars, trying to make sense of the universe's grand design, we are faced with an essential puzzle. What is the true nature of space itself? Space, that vast and seemingly infinite expanse in which everything exists, is not just an empty vacuum as we once thought. It is a dynamic, malleable entity, shaped by forces far beyond our immediate comprehension. The fabric of spacetime itself can bend, stretch, and warp, and understanding how space works is key to understanding the very nature of the universe. At the core of this mystery lies a concept that has been a central theme in modern physics: general relativity. When Albert Einstein introduced his theory of general relativity in the early 20th century, he radically changed our perception of space and time. According to Einstein, space is not an inert stage on which events unfold, but an active participant in the cosmic drama. It is a four-dimensional fabric, spacetime, that is warped by the presence of mass and energy. The more massive an object is, the more it curves the space around it, creating what we perceive as gravity. This idea fundamentally altered how we view the universe. Before general relativity, the prevailing theory of gravity, developed by Isaac Newton, treated space as a kind of empty stage where objects acted upon each other through invisible forces. In Newton's model, gravity was a force that acted at a distance, with no regard for the structure of space itself. However, Einstein's theory showed that gravity was not a force at all, but a curvature in the fabric of spacetime itself. In this new framework, the Earth doesn't simply exert a force on an apple to make it fall. Rather, the mass of the Earth curves spacetime in such a way that the apple follows a path dictated by this curvature. The same principle governs the motion of planets around the Sun, the movement of light around stars, and the warping of spacetime near black holes. This idea of space as a dynamic, malleable entity is both awe-inspiring and bewildering. Space is not just a passive void where events happen, but an active participant in the evolution of the cosmos. It is a fluid medium, constantly shifting and changing, and its very structure is shaped by the mass and energy of the objects within it. This realization forces us to rethink our understanding of the universe at the most fundamental level. Yet, as revolutionary as general relativity is, it leaves us with a key question: how does spacetime behave at the most extreme scales? When we look into the heart of black holes or the early moments of the universe during the Big Bang, we encounter conditions where the curvature of spacetime becomes so extreme that the laws of physics as we know them break down. In these realms, gravity is so intense that even light cannot escape, and the usual rules of space and time cease to function in any meaningful way. The search to understand space at these extremes has led to some of the most exciting and puzzling theories in modern physics. One of the most intriguing of these is the idea of quantum gravity. While general relativity describes the behavior of spacetime on large scales, such as planets, stars, and galaxies, it does not address the behavior of spacetime at the quantum level, where the strange, probabilistic rules of quantum mechanics take over. Quantum mechanics, the theory that governs the behavior of particles on the smallest scales, suggests that space and time themselves might be quantized, broken down into discrete, indivisible units. If space and time are quantized, then they would not be continuous as we usually think of them, but rather made up of tiny, discrete chunks of spacetime. This would radically change our conception of the universe. Instead of being a smooth, continuous expanse, the fabric of spacetime would be more like a pixelated image, made up of individual pixels of space and time. These pixels would be incredibly small, on the order of the Planck length, a scale so tiny that it is far beyond the reach of current experimental techniques. This idea of a quantized spacetime leads to a mind-bending question. What happens when we try to look at the universe at the smallest scales? If spacetime is made up of discrete units, then at some point, our usual notions of space and time would break down completely. At scales smaller than the Planck length, the very concept of space and time might cease to have any meaning. This suggests that the universe operates on a fundamentally different set of rules at the smallest scales, where the effects of both quantum mechanics and general relativity come into play simultaneously. One of the most profound implications of this idea is that it could help resolve one of the greatest paradoxes in modern physics: the problem of black holes. Black holes are regions of space where gravity is so intense that not even light can escape. According to general relativity, the core of a black hole contains a singularity, a point of infinite density where the curvature of spacetime becomes infinite. At this point, the laws of physics break down, and we are left with a mystery that no current theory can explain. However, if spacetime is quantized, the singularity at the heart of a black hole may not be a true point of infinite density, but rather a region where the structure of spacetime becomes incredibly compressed. This might allow us to reconcile the seemingly contradictory ideas of general relativity and quantum mechanics, and offer new insights into the nature of black holes and the fundamental structure of space itself. Another area where our understanding of space is being pushed to its limits is in the study of the early universe. In the first moments after the Big Bang, the universe was a hot, dense soup of particles, and the curvature of spacetime was extreme. In this primordial state, spacetime was stretched and compressed on incredibly small scales, and the usual laws of physics may not have applied. The search to understand the behavior of spacetime during this period has led to the development of the theory of cosmic inflation. Cosmic inflation proposes that in the first fractions of a second after the Big Bang, the universe expanded at an exponentially rapid rate, stretching from a microscopic point to a vast, nearly infinite expanse. This expansion smoothed out any irregularities in the early universe and set the stage for the formation of the structures we see today. The theory of inflation provides a possible solution to some of the major mysteries of the universe, such as the uniformity of the cosmic microwave background radiation and the distribution of galaxies in the universe. However, it also raises new questions about the nature of spacetime itself during this early period, when the universe was in a state of extreme expansion. As we continue to push the boundaries of our understanding, the nature of space remains one of the most profound and mysterious questions in physics. We know that space is not a passive void but an active participant in the cosmic drama, shaped by the forces of gravity and the energy of the objects within it. We know that spacetime can bend, stretch, and warp, and that the rules governing it change at the most extreme scales. But beyond this, we are still left with many questions. What happens when we reach the smallest scales of space and time? How does space behave at the heart of black holes or in the first moments of the universe? What is the true nature of spacetime, and can we ever truly comprehend its structure? These questions are at the forefront of modern physics, and as we continue to explore the universe, we may one day uncover answers that will forever change our understanding of reality. For now, however, space remains a vast and mysterious frontier, one that continues to challenge our most basic assumptions about the nature of the cosmos. The more we learn, the more we realize how little we know, and this paradox, this infinite mystery, is what makes the study of space so endlessly fascinating. As we stand at the crossroads of scientific exploration, attempting to answer some of the most profound questions about the universe, we are confronted with a truly baffling paradox. The universe, as vast and awe-inspiring as it is, seems to be dominated by forces and phenomena that remain invisible to us, forces that govern the cosmos in ways we do not yet fully understand. These elusive entities, dark matter and dark energy, constitute the majority of the universe, yet their very existence challenges everything we thought we knew about the cosmos. Dark matter and dark energy are not merely abstract theoretical constructs. They are real, fundamental aspects of the universe that we are only beginning to comprehend. The concept of dark matter was first introduced in the early 20th century when astronomers observed that the visible matter in galaxies was not enough to explain the gravitational effects they were witnessing. Galaxies seemed to be spinning too quickly, and their outer stars were orbiting at speeds that defied Newtonian physics. According to traditional gravitational theory, the outer edges of galaxies should not have been able to stay intact because the stars on the outskirts should have been flung out into space. Yet, they remained bound to the galaxy's center, suggesting the presence of something invisible, exerting a gravitational pull strong enough to keep them in place. This unseen force was given the name dark matter. While it doesn't emit, absorb, or reflect light, making it completely undetectable by conventional means, it has mass and its gravitational effects can be observed. Scientists know dark matter exists because of how it affects the motion of galaxies and galaxy clusters. In fact, dark matter is thought to make up around 27% of the total mass energy content of the universe. Yet, despite decades of research, we still don't know exactly what it is made of. We know it interacts with regular matter through gravity, but it does not interact with electromagnetic forces, the forces responsible for light and radiation, which means it doesn't emit or absorb light. This absence of detectable radiation makes dark matter incredibly difficult to detect directly. There are several candidates for what dark matter might be, though none have been conclusively proven. The most widely accepted theory involves weakly interacting massive particles, or WIMPs. These hypothetical particles are predicted to be relatively heavy and interact only weakly with regular matter, making them incredibly difficult to detect. WIMPs could be everywhere, yet we would never know they were there unless we could find a way to detect their very subtle interactions with normal matter. Other theories propose that dark matter could be made up of axions, incredibly light and elusive particles, or even primordial black holes formed in the early moments after the Big Bang. But while dark matter is a truly perplexing enigma, it is by no means the most puzzling mystery we face in the universe. That dubious honor belongs to dark energy, an even more elusive force that appears to be driving the accelerated expansion of the universe. Whereas dark matter has been shown to have a gravitational pull, dark energy seems to have the opposite effect. It pushes galaxies apart, causing the expansion of the universe to speed up over time rather than slowing down due to gravity. The discovery of dark energy, made in the late 1990s through the observation of distant supernovae, was one of the most profound and unexpected developments in modern cosmology. Astronomers had assumed that the expansion of the universe, which began with the Big Bang, would eventually slow down due to the pull of gravity. However, when they observed the light from very distant supernovae, they found that the expansion of the universe was actually accelerating. This startling revelation led to the conclusion that something must be causing the expansion to speed up, and that something was dubbed dark energy. Dark energy is now believed to constitute about 68% of the total mass energy content of the universe, making it the dominant force shaping the evolution of the cosmos. Yet, we know almost nothing about what dark energy is or how it operates. It seems to be a property of space itself, something that exists throughout the universe rather than being localized in specific regions. Dark energy is thought to have a constant energy density, meaning it does not dissipate as the universe expands. In fact, the more the universe stretches, the more dark energy becomes influential. This is a truly mind-boggling concept. As space itself grows, dark energy seems to get stronger, pushing galaxies farther and farther apart. Theories about the nature of dark energy abound, but none have been conclusively proven. One possibility is that dark energy is a manifestation of the cosmological constant, a term originally introduced by Einstein in his equations of general relativity. The cosmological constant was initially proposed by Einstein to account for a static universe, a universe that was neither expanding nor contracting. After the discovery that the universe was indeed expanding, Einstein discarded the idea, calling it his biggest blunder. Yet, in light of the discovery of dark energy, some scientists have suggested that the cosmological constant might be a real property of space itself, a kind of energy that permeates the entire cosmos and drives the accelerated expansion. Another theory is that dark energy could be related to a more exotic form of energy, such as quintessence. Quintessence suggests that dark energy is not a constant but rather a dynamic field, capable of changing over time and space. This would imply that the rate of expansion of the universe could change in the future, potentially leading to a slowing down or even a reversal of the expansion. While quintessence offers a compelling explanation, it remains just one of many possibilities. The truth is, we are far from understanding dark energy, and its discovery has opened up a whole new set of questions about the nature of the universe. How can a force that has no clear physical origin have such a profound impact on the universe's fate? What role does dark energy play in the ultimate destiny of the cosmos? Could dark energy be a temporary phenomenon, one that will dissipate as the universe evolves? Or is it a fundamental property of space that will continue to dominate the universe's expansion for all of time? As scientists race to understand dark matter and dark energy, they face a monumental challenge. Detecting these elusive phenomena requires innovative new technologies and approaches. For dark matter, scientists are developing highly sensitive detectors that attempt to pick up the rare interactions between dark matter particles and ordinary matter. Experiments like those conducted at the Large Hadron Collider, LHC, and the underground facilities designed to detect dark matter are pushing the boundaries of what is possible. For dark energy, astronomers are using observations of supernovae, galaxy clusters, and the cosmic microwave background radiation to probe the accelerated expansion and gain insights into its nature. Despite the challenges, we continue to make progress. New observations and data from cutting-edge space telescopes like the James Webb Space Telescope promise to bring us closer to uncovering the secrets of dark matter and dark energy. But even as we inch toward understanding, we are confronted with the humbling realization that we are just scratching the surface of a much deeper mystery. Dark matter and dark energy represent not only an incredible scientific puzzle but also a cosmic reminder of how much we still have to learn about the universe. They force us to confront the limits of our knowledge and to reconsider our place in the cosmos. In many ways, the discovery of dark matter and dark energy has opened a new frontier in science, one that will continue to captivate our imaginations for generations to come. These mysterious forces shape the universe in ways we can barely begin to comprehend, and yet they remain hidden from our direct view. They may be the key to unlocking some of the deepest secrets of the cosmos, offering us a glimpse into the very nature of reality itself. Until then, the quest to understand dark matter and dark energy will continue to drive the search for answers, pushing the boundaries of human knowledge and challenging our understanding of the universe in ways we are only beginning to appreciate. As we continue to search for meaning in the vast expanse of the cosmos, we begin to confront one of the most fundamental questions. Is the universe a single, interconnected whole, or is it a collection of isolated systems, existing independently of one another? The idea that everything in the universe might be connected, on both the largest and smallest scales, has fascinated philosophers, scientists, and thinkers for centuries. As we venture deeper into the heart of this mystery, the notion of the universe as a network begins to emerge, and it challenges everything we thought we knew about space, time, and the fundamental laws of nature. For much of human history, the universe was perceived as a static, unchanging collection of objects that were separated by vast distances. The stars were seen as distant points of light in the night sky, and the planets were simply objects that orbited our sun, isolated in their own orbits. The concept of interconnectedness wasn't a dominant idea. Rather, the universe was often thought of as a machine, with each part operating independently from the others. This view was reinforced by Newtonian physics, which treated space as an empty stage in which objects interacted according to fixed laws. Gravity, for example, was seen as a force acting across empty space, with no regard for the fabric of space itself. However, the advent of general relativity in the early 20th century challenged this notion. Einstein's theory suggested that space itself was not empty, but a dynamic, warping fabric that could bend, stretch, and twist in response to mass and energy. In this model, space is not simply a container for matter. It is intimately tied to the matter it contains. The fabric of spacetime is shaped by the objects within it, and, in turn, it influences the motion of those objects. This realization was revolutionary. It suggested that the universe is not a collection of isolated parts, but rather a deeply interconnected system, where everything is influenced by everything else. But the implications of this insight extend far beyond the realm of general relativity. As scientists began to explore the structure of the universe on the largest scales, they discovered something truly extraordinary. The universe itself appears to be a vast, interconnected web. Galaxies are not scattered randomly throughout space, but instead they are organized into clusters and superclusters, interconnected by vast cosmic filaments of dark matter and gas. These filaments form a cosmic web that stretches across the universe, with galaxies and clusters of galaxies connected in a network of gravitational bonds. This network, which has been revealed through extensive surveys of the cosmos, is one of the most surprising discoveries of modern cosmology. It shows that the universe is not just a collection of isolated objects, but rather a vast, interconnected structure in which everything is tied together through the invisible threads of gravity and dark matter. This cosmic web is not only a physical structure but a reflection of the way that the universe operates on the largest scales. It suggests that the universe is much more than the sum of its parts. It is a single, integrated system in which every galaxy, every star, and every planet is connected to every other object by the fabric of spacetime itself. One of the most intriguing aspects of this cosmic network is the role of dark matter. While dark matter cannot be directly observed, its presence is inferred through its gravitational effects on visible matter. Dark matter acts like a scaffolding for the structure of the universe, providing the gravitational pull that holds galaxies and galaxy clusters together. It is this invisible dark matter that forms the backbone of the cosmic web, shaping the way that galaxies are distributed and interacting with one another. Without dark matter, the universe as we know it would look radically different. galaxies would not form in the same way, and the large-scale structure of the universe would be far less cohesive. This realization, that dark matter is the key to understanding the interconnectedness of the universe, raises a number of important questions. What exactly is dark matter, and how does it interact with ordinary matter? While we can infer its presence through its gravitational effects, we still don't know what dark matter is made of or how it behaves on a fundamental level. Is it a type of particle, or is it some kind of exotic substance that we have yet to discover? The search for dark matter has become one of the most pressing questions in modern physics, and its discovery could have profound implications for our understanding of the cosmos. If dark matter is truly the scaffolding that holds the universe together, then understanding its properties could help us unlock some of the deepest secrets of the universe itself. But the story of the cosmic web is not just about galaxies and dark matter. It also has profound implications for our understanding of the nature of time and space. The fact that galaxies are interconnected through invisible filaments of dark matter and gravity suggests that space itself is not a static backdrop against which events occur. Instead, space is a dynamic, interconnected medium in which every part of the universe is tied to every other part. This idea echoes the insights of general relativity, which tells us that space is not empty, but a malleable, interconnected fabric that responds to the presence of mass and energy. In a way, the cosmic web can be thought of as a reflection of the interconnectedness of all things. Just as the galaxies are linked together by the invisible threads of dark matter and gravity, so too are we connected to the universe in ways we cannot yet fully comprehend. The universe is not a cold, impersonal machine. It is a living, breathing system, constantly evolving and changing. Every object in the universe, from the smallest particle to the largest galaxy, plays a role in the grand cosmic drama. And just as the galaxies are woven together in a vast cosmic web, so too are we, as individuals, part of a greater network of existence that transcends our immediate experience. This interconnectedness also has deep philosophical implications. If the universe is truly a vast network, then perhaps everything in the universe is somehow connected on a deeper, more fundamental level. Could it be that everything in the cosmos, from the smallest subatomic particles to the largest structures, is linked by an invisible thread of influence? This idea has echoes of ancient philosophical concepts, such as the notion of the web of life, or the oneness of the universe. It suggests that the universe is not a collection of isolated objects, but a single, unified entity in which everything is interrelated. For centuries, philosophers have grappled with the idea of interconnectedness. From the ancient Greeks to Eastern philosophies, the notion that everything in the universe is connected has been a central theme in many spiritual and philosophical traditions. Modern physics, with its discoveries of the cosmic web and the interconnectedness of galaxies, may be providing a scientific basis for these ancient ideas. It suggests that, on the largest scales, the universe is not a collection of random objects, but a deeply integrated system, in which every part is influenced by every other part. Yet, as we continue to probe the nature of this interconnected universe, we are faced with more questions than answers. What is the true nature of the cosmic web, and how does it influence the behavior of galaxies and other cosmic structures? What role does dark energy play in this vast interconnected system, and how does it shape the expansion of the universe? How can we reconcile the idea of an interconnected universe with the vast distances between galaxies, and the apparent isolation of individual objects within space? These questions are not easily answered, but they point to one of the most profound truths about the cosmos. The universe is far more complex and interconnected than we could have ever imagined. The more we explore the universe, the more we realize how little we truly know. The cosmic web is a reminder that everything in the universe, from the smallest particles to the largest galaxies, is part of a larger, interconnected whole. And as we continue to explore the mysteries of space, we are not just learning about the universe, but about our place within it, our connection to the cosmos and to the very fabric of reality itself. As we continue to peel back the layers of the cosmos, one of the most perplexing and thrilling questions that remains is, what is the ultimate fate of the universe? The grand story of the cosmos, from its birth in the Big Bang to the infinite expanse we see today, is a tale still unfolding, yet its ending is shrouded in mystery. With each passing year, new discoveries and theories emerge, offering tantalizing glimpses of how the universe might evolve and eventually reach its conclusion. Yet, despite our growing understanding, we are still far from certain about what the final chapter of this cosmic narrative will look like. For centuries, the fate of the universe was tied to a simple concept: that the universe was static and unchanging. The idea of a universe with a definite beginning and end was largely outside the scope of human imagination. That changed with the advent of modern cosmology, particularly after the discovery that the universe is expanding. In the early 20th century, Edwin Hubble's observation that galaxies were receding from us, a discovery that would eventually lead to the formulation of Hubble's law, made it clear that the universe is not static, but is, in fact, growing larger with each passing moment. This revelation forced scientists to reconsider not only the origin of the universe but also its eventual fate. Initially, the prevailing theory was that the universe would continue to expand forever. This idea, known as the Big Freeze, suggests that as space stretches further and further apart, galaxies, stars, and planets would be isolated from one another, with the universe gradually becoming colder and more desolate. Stars would burn out, and the remaining energy would dissipate into an ever-expanding void, leaving behind a frozen, dark, and lifeless universe. It's a vision of cosmic entropy, where all systems eventually reach a state of maximum disorder and stillness. However, this seemingly inevitable end was complicated by a discovery in the late 1990s that no one expected. The expansion of the universe is accelerating. This astonishing realization came from observations of distant supernovae. Scientists had assumed that the gravitational pull of matter in the universe would eventually slow the expansion of the cosmos. Instead, the supernovae data revealed that not only was the universe still expanding, but the expansion was accelerating at an ever-increasing rate. This observation led to the identification of dark energy, an enigmatic force that is driving the accelerated expansion. The discovery of dark energy has fundamentally changed our understanding of the universe's fate. Whereas once it seemed the expansion might slow and eventually reverse, leading to a big crunch, a scenario where the universe would collapse in on itself, the presence of dark energy suggests that the universe may continue to expand forever, speeding up as it goes. The idea of the Big Freeze is now seen as one of the most likely scenarios for the universe's ultimate end, but it is far from the only possibility. Another theory, known as the Big Crunch, posits that the expansion of the universe will eventually slow down and reverse. This reversal could occur if the gravitational pull of all the matter in the universe is strong enough to halt the expansion and cause everything to collapse back in on itself. In this scenario, galaxies, stars, and eventually all matter would be drawn into a singularity, a point of infinite density. The universe would end in a violent and catastrophic implosion, much like the reverse of the Big Bang. The Big Crunch has largely fallen out of favor in light of recent evidence pointing to the dominance of dark energy, which seems to be driving the universe apart rather than pulling it together. However, there are still uncertainties about the nature of dark energy. Some versions of dark energy, especially those described by models of quintessence, suggest that it could change over time, and that the expansion of the universe might slow down or even reverse in the distant future. If this were the case, the Big Crunch could still be a potential outcome, albeit one that seems less likely in the present moment. A more recent proposal that has emerged from cosmological theories is the idea of the Big Rip. This scenario suggests that if dark energy continues to increase in strength over time, the expansion of the universe could accelerate to the point where it tears apart everything in its path. In the Big Rip scenario, galaxies, stars, planets, and even atoms would be progressively ripped apart as the expansion rate surpasses the forces that hold everything together. The ultimate consequence of this would be the disintegration of all matter in the universe, leaving behind only a vast, empty, expanding void. The Big Rip presents an even more violent and final end to the universe than the Big Freeze, and it hinges on the behavior of dark energy in the distant future. Beyond these three major scenarios, Big Freeze, Big Crunch, and Big Rip, there are other, more speculative theories that attempt to explain how the universe could end. One such idea is the possibility of a heat death, a concept closely related to the Big Freeze. According to the second law of thermodynamics, the universe is heading toward a state of maximum entropy, where energy is evenly distributed and no work can be done. As stars burn out and energy is dispersed across an increasingly larger space, the universe will approach a state where all processes cease, and no more thermodynamic work is possible. The universe will reach a state of perfect thermodynamic equilibrium, where everything is uniformly cold and lifeless. Another, more philosophical view posits that the universe might not have an end at all. Some theories suggest that the universe could experience a cycle of rebirths, with each end giving way to a new beginning. This cyclical model, sometimes referred to as the oscillating universe theory, suggests that the universe could undergo repeated cycles of expansion and contraction. Each cycle would begin with a Big Bang and end with a Big Crunch, only to be followed by another Big Bang, creating an endless loop. While this model is appealing in its sense of cosmic renewal, it faces significant challenges in terms of current observational evidence, and the question of whether it can hold up to scrutiny remains an open debate in cosmology. Yet, despite the multitude of theories and possibilities, one truth seems to remain clear. The end of the universe, whatever it may look like, is a long way off. The current expansion of the universe is accelerating, and the rate of expansion is likely to continue for billions of years. Stars still burn brightly in the night sky, galaxies continue to dance and collide, and new planets are born in distant corners of the cosmos. Even in the most likely scenarios of cosmic endings such as the Big Freeze or the Big Rip, we are still talking about timescales on the order of trillions of years, far beyond the span of human civilization. As we peer into the future, we are reminded that the ultimate fate of the universe is not just a scientific question, but a deeply philosophical one. What does it mean for us, as human beings, to contemplate the end of everything we know and love? And what does it mean for our place in the cosmos? The universe's final chapter is something that may never fully be understood in our lifetime, but that doesn't mean our search for answers is meaningless. In fact, it is perhaps in our attempt to understand the universe's fate that we come to understand our own place within it. The universe's ultimate end, whether it be through the quiet cold of the Big Freeze, the catastrophic implosion of the Big Crunch, or the violent tearing apart of the Big Rip, is an event that will unfold long after humanity is gone. Yet, in our search for meaning, in our quest for understanding, we are participating in the grand story of the cosmos. Our desire to know, to explore, and to understand the universe's fate is part of what makes us human. In the face of such unimaginable time scales, we may find our true meaning not in the knowledge of the end, but in the pursuit of discovery itself. For as long as the stars continue to burn, and the mysteries of the universe remain, our journey into the cosmos will never truly be over. As we stand on the precipice of understanding the vast and infinite cosmos, we are forced to confront one of the most fundamental questions of all. What is the true nature of time? Time, that intangible force that shapes every moment of our lives, has long been a subject of fascination for scientists, philosophers, and poets alike. Yet, despite centuries of exploration and debate, time remains one of the greatest mysteries of the universe. It governs everything from the motion of planets to the aging of stars, and yet, it defies our ability to fully grasp its true essence. For most of human history, time was thought to be a constant, an unchanging backdrop against which the events of the universe unfolded. It was something that ticked away uniformly and predictably, from the past to the present and into the future. This conventional view of time was solidified by the work of Isaac Newton, who described time as an absolute, universal flow that applied equally to all things, regardless of their state of motion. Newton's laws of motion and gravitation worked within this framework, and for centuries this view of time as an immutable force seemed to hold true. Time was linear, steady, and separate from the physical world. However, in the early 20th century, Albert Einstein's theory of relativity shattered this simplistic view of time. According to Einstein, time is not an absolute, universal constant but is instead deeply intertwined with the fabric of space itself. The concept of spacetime, as Einstein described it, was revolutionary. Instead of thinking of space and time as separate entities, Einstein proposed that they were part of a single four-dimensional continuum that could bend, stretch, and curve in response to mass and energy. This idea led to the realization that time is not the same for everyone or everywhere in the universe. Einstein's theory showed that time is relative, and it can be affected by both gravity and speed. This phenomenon, known as time dilation, means that time passes differently for observers in different situations. For example, if you were to travel close to the speed of light, time would slow down for you relative to someone who remains stationary. Similarly, time passes more slowly for objects near massive bodies like stars or black holes, because the intense gravitational pull of these objects causes spacetime to warp. These insights from relativity have been confirmed through numerous experiments and observations, and they have revolutionized our understanding of time. Yet, even with Einstein's groundbreaking work, time remains a slippery and elusive concept. Despite its central role in our understanding of the universe, we still do not fully understand its origins, its nature, or its ultimate direction. One of the most perplexing questions about time is why it seems to move in one direction, from past to present to future. The concept of the arrow of time refers to the fact that time appears to have a distinct direction. Events unfold in a linear sequence and we cannot reverse the flow of time. We remember the past but cannot change it, and we anticipate the future but it has not yet occurred. This one-way progression of time is a fundamental aspect of our experience, but why time should flow in this direction and not the other way remains one of the great mysteries of physics. One of the most widely discussed explanations for the arrow of time is the second law of thermodynamics, which states that entropy or disorder tends to increase over time. In simple terms, this law suggests that systems in the universe naturally evolve from states of lower entropy to states of higher entropy. A glass of water that is initially cold will eventually warm to the temperature of its surroundings, for example, and this process is irreversible. Over time, the universe as a whole is moving toward a state of maximum entropy, where all energy is evenly distributed and no further work can be done. This increasing disorder gives time its direction, as events naturally unfold in the direction of greater chaos. But while the second law of thermodynamics explains the one-way flow of time in terms of entropy, it does not tell us why time itself exists in the first place. Why should the universe have a time dimension at all? Why do we experience time as something that flows, rather than as a static, unchanging backdrop? These questions have perplexed scientists and philosophers for centuries. One possibility is that time is an intrinsic feature of the universe, woven into the very fabric of spacetime. In this view, time exists as a fundamental aspect of the universe, inextricably linked to the physical laws that govern the cosmos. However, this raises further questions. Is time a real entity, or is it merely a human construct, a way of organizing our experience of the world? Another possibility is that time is an emergent property of the universe, a phenomenon that arises from the underlying dynamics of space and matter. Some theories suggest that time might be a product of the way that matter and energy interact on the quantum level. In this view, time would not be a fundamental feature of the universe but a byproduct of the way particles and forces evolve. The idea that time is emergent rather than fundamental challenges our conventional understanding of reality, and it has led to a number of fascinating and speculative theories, including those that involve the nature of quantum gravity. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, has its own peculiar relationship with time. In quantum theory, particles do not have definite positions or velocities until they are observed. Instead, they exist in a superposition of probabilities. This probabilistic nature of quantum particles raises the question of how time fits into the picture. If the future is uncertain and determined by probabilities, does time exist in the same way at the quantum level as it does in our everyday experience? Some quantum theories, such as the concept of quantum entanglement, suggest that time may not be as linear or uniform as we perceive it to be. In certain situations, particles can become entangled, meaning that their states are linked no matter how far apart they are. This entanglement seems to challenge our classical understanding of time, as the particles appear to affect each other instantaneously, regardless of the distance between them. This strange behavior at the quantum level raises important questions about the true nature of time and whether our experience of it is a fundamental feature of reality, or merely an illusion. Yet, despite all these fascinating theories, we still don't have a complete understanding of time. We do not know why time began with the Big Bang or what its ultimate fate might be. Is time itself finite like the universe, or is it infinite, extending endlessly in both directions? Some theories suggest that time itself may have begun at the moment of the Big Bang, emerging alongside space in a singular event. This idea suggests that time did not exist before the Big Bang, and that the flow of time itself is tied to the history of the universe. If time began at the Big Bang, then it may one day come to an end, perhaps at the heat death of the universe or in some other unknown event. Other theories suggest that time may be cyclical, repeating in endless loops. This idea, known as the block universe theory, proposes that time is not something that flows but is rather a frozen block, where the past, present, and future all exist simultaneously. In this view, our perception of time's flow is merely an illusion, and all events are already laid out in a single, unchanging block of time. This concept has profound implications for free will and the nature of consciousness, suggesting that our sense of free choice may be an illusion as well. Time may be one of the most fundamental and elusive aspects of reality, and yet, it may also be one of the most unknowable. As we continue to explore the mysteries of the universe, we may never fully understand time in the way we understand other physical phenomena. But that does not diminish the wonder and awe that time evokes. It is through our experience of time that we come to understand the very fabric of existence, how the universe began, how it evolves, and how we, as conscious beings, navigate through it. Time is both a mystery and a guide, a force that governs all things, yet remains forever beyond our full comprehension. It is one of the deepest puzzles of the cosmos, and it may hold the key to understanding the true nature of reality itself. In the vastness of the cosmos, we often find ourselves grappling with another profound and seemingly paradoxical question. What is the true nature of reality itself? As we delve deeper into the mysteries of space, time, and the universe, it becomes increasingly clear that reality is not as simple as it might initially appear. It is a complex tapestry, woven together by forces and laws that govern everything from the smallest subatomic particles to the largest galaxies, yet its fundamental nature remains elusive. What we perceive as real is often a limited, imperfect interpretation of a far more intricate and dynamic reality, one that may be vastly different from the way we experience it through our senses. Throughout history, different philosophical and scientific perspectives have offered competing visions of what constitutes the real world. Ancient philosophers such as Plato argued that the physical world is but a shadow of a deeper, ideal realm, one that could only be understood through the intellect, not the senses. For Plato, the world of forms was the ultimate reality, and the material world was a mere reflection of this higher truth. This idea of reality being something beyond the immediate physical world has echoed through centuries of thought, and it continues to influence modern scientific and philosophical debates. Yet, the more we explore the nature of the universe, the more we find that reality is far more complicated than Plato or other early philosophers could have imagined. In the early 20th century, the advent of quantum mechanics brought with it an entirely new understanding of reality, one that shattered many of the traditional assumptions that had guided scientific thought for centuries. At the quantum level, particles exist in multiple states at once, in a phenomenon known as superposition. This means that particles like electrons do not have a definite position or velocity until they are observed, and until that moment, they exist as a probability cloud of all possible states. This strange behavior challenges our conventional notions of reality, suggesting that the very fabric of existence is far more fluid and uncertain than we once believed. This revelation, first brought to light by the pioneering work of physicists like Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, has led to a profound re-evaluation of what reality even means. In the quantum world, reality seems to be shaped by observation and measurement. The act of looking at a particle changes its state, collapsing its wave function into a specific position or velocity. This idea has led to various interpretations of quantum mechanics, each offering a different perspective on the relationship between the observer and the observed. One of the most famous and controversial of these interpretations is the Copenhagen interpretation, which posits that quantum systems exist in a state of potentiality until they are observed, at which point they collapse into a definite state. This interpretation suggests that reality is not a fixed, objective entity but something that is dependent on observation. In other words, the universe exists in a state of flux, and its true nature is only revealed when we interact with it. The idea that reality is shaped by observation has led some to wonder whether consciousness itself plays a fundamental role in creating the universe we perceive. If our very act of observing the world around us determines the state of reality, then could it be that our minds are intrinsically connected to the cosmos in ways that we are only beginning to understand? This concept takes us into the realm of quantum consciousness, a field of study that explores the possibility that consciousness itself arises from quantum processes. Some theorists argue that the brain operates on a quantum level, with neurons and synapses interacting in ways that are consistent with the principles of quantum mechanics. If true, this would mean that our consciousness is not just a product of classical brain activity but is somehow intertwined with the fundamental workings of the universe at the deepest levels. While this idea remains speculative and controversial, it raises profound questions about the nature of reality, the mind, and the universe itself. Beyond the quantum world, another branch of science that has revolutionized our understanding of reality is the theory of relativity. Albert Einstein's special and general theories of relativity fundamentally altered our conception of space and time. According to relativity, space and time are not separate, absolute entities but are part of a single, interconnected fabric known as spacetime. This fabric can be warped and distorted by the presence of mass and energy, and the curvature of spacetime determines how objects move through it. The familiar, Newtonian idea of space as an empty, passive backdrop against which events occur is replaced by a view of space as an active, dynamic participant in the unfolding of the cosmos. This understanding of spacetime has profound implications for our understanding of reality. It suggests that the structure of the universe is not simply an empty stage for the drama of matter and energy to play out. It is an active, living entity that shapes the very events that take place within it. Spacetime is not a passive backdrop. It is a participant in the unfolding of events, bending and stretching in response to the presence of mass and energy. This dynamic view of spacetime challenges our conventional understanding of reality, which is often grounded in the idea that space and time are fixed, unchanging, and independent of the material world. Moreover, the concept of spacetime also gives rise to the idea that the future, the present, and the past are all part of a single unified structure. In the theory of relativity, there is no universal, objective present moment that is experienced by all observers in the same way. Instead, time is relative to the observer's frame of reference, and the concept of simultaneity breaks down. This suggests that our perception of time, our sense of a linear flow from past to present to future, is a subjective experience, tied to our position in the universe and the way we interact with the fabric of spacetime. This idea calls into question the nature of temporal reality and suggests that the flow of time may not be as absolute and objective as we have always believed. As we step back and examine the larger structure of the universe, we are confronted with yet another layer of complexity in our understanding of reality. The universe as we observe it is not a static or isolated entity, but is in a constant state of flux. Galaxies are moving, stars are born and die, and space itself is expanding. The very fabric of reality is subject to the dynamic forces of gravity, dark energy, and dark matter. These unseen and mysterious forces shape the universe in ways that we are only beginning to understand. Yet, despite the overwhelming complexity of the cosmos, we experience reality as a coherent, orderly system, one that obeys the laws of physics and is governed by predictable patterns. This coherence gives us a sense of control and understanding, even as we realize that the universe is far more intricate and elusive than we can fully comprehend. At the heart of this complexity lies a profound paradox, that the more we discover about the universe, the more we realize how little we truly know. Every scientific breakthrough, every new theory, reveals new questions, new mysteries that remain unsolved. The universe is not a static, fixed reality but a constantly evolving, ever-changing system, one that seems to defy our attempts to fully understand it. And yet, despite the uncertainty and mystery that pervade our exploration of the cosmos, there is something deeply satisfying in the pursuit of knowledge itself. The journey toward understanding reality, even if it leads to more questions than answers, is a path that brings us closer to the essence of existence. As we continue to explore the mysteries of space, time, and the universe, we are not just searching for answers about the cosmos, but also about ourselves, our place within this vast, ever-changing reality. As we turn our gaze to the stars and contemplate the vast expanse of the universe, we are forced to confront a profound and unsettling question. Are we truly alone in the cosmos? This question, ancient and timeless, has occupied the minds of philosophers, scientists, and dreamers for millennia. For as long as humanity has looked to the heavens, we have wondered whether there are other forms of life out there, somewhere in the infinite reaches of space. From the earliest mythologies to the cutting-edge theories of modern astrophysics, the search for life beyond Earth has been one of our greatest quests. Yet, despite centuries of speculation, the question remains unanswered. In our quest for understanding, we have only begun to scratch the surface of this vast and seemingly infinite mystery. On one hand, the universe is so overwhelmingly large, consisting of billions of galaxies, each containing billions of stars and potentially even more planets, that the likelihood of life emerging elsewhere seems almost certain. On the other hand, the absence of direct evidence for extraterrestrial life presents a deeply troubling conundrum. How is it possible that, in all this cosmic vastness, we have yet to find any definitive signs of life beyond Earth? For much of human history, the idea of life beyond our planet was speculative at best, and outright heretical at worst. Ancient civilizations had their own stories and beliefs about the cosmos, but they often envisioned Earth as the center of the universe, with other worlds as distant and inconsequential. The notion that life could exist elsewhere was simply too radical to entertain seriously. With the advent of modern science, however, the question began to take on new significance. In the 16th century, astronomers like Copernicus and Galileo began to challenge the geocentric view of the universe, and in doing so, they opened the door to the possibility that Earth was not the center of everything. The discovery that planets orbit the Sun and not the Earth was a crucial turning point in our understanding of the cosmos. Yet, even with this new perspective, the idea of other worlds harboring life remained speculative. The real breakthrough came in the mid-20th century with the discovery of the vast number of exoplanets, planets orbiting stars other than our Sun. With the advent of modern telescopes and space-based observatories, scientists began to detect planets in other star systems that were similar in size and temperature to Earth, some even lying within the habitable zone, where conditions might be right for liquid water to exist. The discovery of these exoplanets radically shifted our understanding of the universe. No longer did Earth seem to be an isolated anomaly. Rather, it appeared that planets capable of supporting life might be relatively common. This discovery gave rise to the field of astrobiology, the study of life in the universe, and with it, the hope that we might one day find evidence of extraterrestrial life. Scientists began to search for biosignatures, or signs of life, in the atmospheres of distant planets. They studied the chemical compositions of exoplanet atmospheres for telltale signs of biological activity, such as oxygen, methane, and carbon dioxide, gases that are commonly associated with life on Earth. The possibility that such signs might eventually be detected has led to renewed optimism that we may one day find evidence of life beyond Earth. However, despite the growing number of potentially habitable planets, the search for life beyond our world has yielded little concrete evidence. Over the past few decades, thousands of exoplanets have been discovered, but none have shown definitive signs of life. For all the billions of planets that dot the galaxy, none have yet revealed a clear, unmistakable signal indicating the presence of extraterrestrial life. This lack of evidence has led to a phenomenon known as the Fermi paradox, named after the famous physicist Enrico Fermi, who famously asked, "Where is everybody?" Given the vastness of the universe and the apparent abundance of potentially habitable planets, why have we not yet encountered any signs of intelligent extraterrestrial civilizations? The Fermi paradox poses a stark contrast to the optimism that once surrounded the search for life. If intelligent civilizations are so common, why has humanity not detected any radio signals, space probes, or any other form of communication from other civilizations? This question has puzzled scientists for decades, and a wide array of theories has been proposed to explain the paradox. One possibility is that extraterrestrial civilizations simply do not exist, or if they do, they are so far apart in space and time that contact is nearly impossible. The vast distances between stars, even in our relatively nearby stellar neighborhood, present an enormous challenge to interstellar communication or travel. Even if advanced civilizations exist, they might be so distant that any signals they send would take thousands, if not millions, of years to reach us. Furthermore, the possibility exists that such civilizations may have self-destructed before they could make contact, or that they may have evolved in ways that make communication with them impractical or even incomprehensible. Another theory suggests that extraterrestrial civilizations might be intentionally avoiding us, either out of caution or indifference. The idea of a zoo hypothesis proposes that advanced civilizations are aware of humanity but have chosen not to contact us, perhaps for ethical reasons, similar to how humans might avoid interfering with the development of a primitive society. Alternatively, the prime directive hypothesis, popularized by the Star Trek franchise, argues that extraterrestrial civilizations may adhere to a policy of non-interference, allowing civilizations like ours to evolve on their own without external influence. A more sobering possibility is that we are simply not looking in the right way. Perhaps we are using the wrong methods or technologies to detect extraterrestrial life. Our search for life has largely focused on finding Earth-like planets with conditions similar to our own. Yet, life could exist in forms radically different from what we are accustomed to, possibly in environments that we do not yet understand. For example, some scientists speculate that life could exist in the clouds of Venus, or beneath the icy crusts of moons like Europa and Enceladus, where liquid water might exist in subsurface oceans. These environments, though extreme by Earth standards, may harbor life in forms that are unlike anything we have encountered on our planet. Furthermore, our search for extraterrestrial intelligence, SETI, has focused primarily on detecting radio signals or other forms of communication that are based on the assumption that alien civilizations would use technology similar to ours. However, it is entirely possible that advanced civilizations use entirely different forms of communication, or that they have evolved beyond the need for radio signals or space probes. The universe is vast, and our methods of detecting extraterrestrial life are limited by our current understanding of technology and communication. In addition to these possibilities, there is a more radical theory that suggests that extraterrestrial life is not just rare, but might be fundamentally different from what we envision. Some thinkers propose that we might be part of a larger, interconnected cosmic ecosystem of life that operates on principles entirely foreign to us. Perhaps extraterrestrial civilizations exist on entirely different planes of existence, beyond our three-dimensional understanding of space and time. This idea raises questions about the nature of consciousness and reality itself, suggesting that there may be forms of intelligence and life that transcend the physical universe as we know it. The search for extraterrestrial life is not just a scientific endeavor, it is also a deeply philosophical one. The discovery of life beyond Earth would have profound implications for our understanding of ourselves and our place in the universe. If we find that we are not alone, it would force us to reconsider our assumptions about the uniqueness of humanity and the centrality of Earth in the cosmos. On the other hand, if we remain alone in the vastness of space, it raises equally profound questions about the nature of life, consciousness, and the purpose of existence. Are we the only conscious beings in the universe, or are we just one small part of a far greater cosmic story? For now, the search for extraterrestrial life continues, fueled by the optimism that one day, the universe will reveal its secrets. With the advancement of new technologies such as the James Webb Space Telescope and other cutting-edge instruments, the hope remains that we will eventually detect the telltale signs of life beyond Earth. Until that time comes, the question of whether we are truly alone in the universe remains one of the most profound and enduring mysteries of our existence. It is a question that will continue to inspire exploration, discovery, and wonder for generations to come. In the ever-expanding search for understanding, one of the most profound questions that has emerged in recent decades revolves around the concept of consciousness. What does it mean to be aware? What is the true nature of consciousness, and how does it arise from the complex interactions of neurons in the brain? As we delve deeper into the mysteries of the mind, we find that consciousness is not just a scientific puzzle, but also a philosophical enigma that has confounded thinkers for millennia. It is the very essence of what it means to be human, yet we remain profoundly uncertain about its origins, its nature, and its place in the universe. Consciousness is the lens through which we experience the world. It is what allows us to perceive, to think, to feel, and to reflect upon our own existence. And yet, despite being at the center of our every experience, consciousness remains largely elusive and difficult to define. It is not something that can be directly observed in the same way as physical objects or measurable phenomena. We cannot see consciousness, touch it, or measure it with the tools we currently possess. Instead, we experience it subjectively, through the veil of our own perception. This subjectivity, the feeling of what it's like to be conscious, has led some philosophers to refer to consciousness as the hard problem, a term popularized by the philosopher David Chalmers. The hard problem of consciousness is simple yet profound. How do physical processes in the brain give rise to subjective experience? How is it that the firing of neurons, the movement of electrical signals, and the release of neurotransmitters can lead to the rich inner world of thoughts, feelings, and sensations that we all know as our conscious experience? This question has stumped philosophers, neuroscientists, and psychologists for centuries, and yet, despite all our advances in understanding the brain, we are still no closer to unraveling the mystery of consciousness. One of the major challenges in understanding consciousness lies in the fact that it cannot be reduced to a simple equation or model. Unlike physical phenomena, which can be described with mathematical precision, consciousness resists such reduction. While we can study the brain and observe which areas are activated during various cognitive tasks, we still do not understand why these brain activities are accompanied by a conscious experience. Why should the firing of neurons be accompanied by the feeling of pain, pleasure, or thought? And why should these experiences be unique to each individual, with no two consciousnesses being exactly alike? Several theories have been proposed to explain the nature of consciousness, but none have proven conclusive. One of the most well-known is the theory of materialism, which posits that consciousness arises from the physical interactions of matter, specifically the neurons in the brain. According to this view, consciousness is simply an emergent property of the brain's complex network of connections. Just as water molecules, when arranged in a certain way, form the property of liquid, so too does the intricate arrangement of neurons give rise to the phenomenon of consciousness. In this framework, consciousness is entirely dependent on the physical structure of the brain and would cease to exist if the brain were damaged or destroyed. Yet, materialism faces significant challenges. One of the key issues is the problem of qualia, which refers to the individual qualities of conscious experience, such as the taste of chocolate, the color red, or the feeling of happiness. While we can describe the physical processes associated with these experiences, such as the firing of neurons in response to sensory stimuli, we cannot explain why these processes should feel a certain way. What is it about the brain's activity that gives rise to the feeling of redness, when we see the color red, or the sensation of pain when we stub our toe? The subjective, qualitative nature of experience seems to resist explanation within the materialist framework, and this has led some to question whether consciousness can truly be explained purely in terms of physical processes. In contrast to materialism, some philosophers and scientists have proposed that consciousness is not just an emergent property of the brain, but rather something fundamental to the universe itself. This view is known as panpsychism, and it suggests that consciousness is a basic feature of reality, akin to space and time. According to panpsychism, everything in the universe, from the smallest particle to the largest galaxy, possesses some form of consciousness, albeit at a very rudimentary level. This idea challenges our conventional understanding of consciousness, suggesting that the mind may not be something that emerges from the brain at all, but rather a property of the universe that exists in some form within all matter. While panpsychism may seem outlandish at first glance, it has gained increasing attention in recent years, particularly among certain philosophers and physicists. One of the most intriguing aspects of panpsychism is that it could provide a solution to the hard problem of consciousness. If consciousness is a fundamental property of the universe, then the subjective experience that we have might simply be the result of a particular arrangement or configuration of this universal consciousness. Just as the complex interactions of atoms give rise to matter, the complex interactions of consciousness at the level of the brain could give rise to the rich, subjective experience we know as human consciousness. Despite its appeal, panpsychism has yet to be widely accepted within the scientific community, and many critics argue that it fails to offer a satisfactory explanation for the nature of consciousness. One of the major challenges is that it is difficult to test or observe consciousness at the level of subatomic particles or in non-living matter. If consciousness is truly a universal property, it should be detectable in some way, but our current scientific tools do not seem equipped to measure or observe consciousness in anything other than human or animal brains. Until we can develop a method for detecting or quantifying consciousness in the broader universe, panpsychism will likely remain speculative at best. A third theory that has gained traction in recent years is integrated information theory (IIT), which posits that consciousness arises from the integration of information within a system. According to IIT, the more interconnected and integrated a system is, the more conscious it becomes. The brain, with its vast network of neurons, is seen as the ultimate example of an integrated information system, and this integration is thought to give rise to conscious experience. In this view, consciousness is not tied to any specific physical substance, but rather to the way information is processed and integrated within a system. This theory has led some to speculate that artificial intelligence, AI, could one day be conscious, provided it possesses the necessary level of information integration. IIT offers an intriguing framework for understanding consciousness, but it too faces significant challenges. One of the key difficulties is that the theory is highly abstract and difficult to apply in practice. While IIT provides a mathematical model for understanding how consciousness might arise from information integration, it is unclear how to test or validate this theory in real-world scenarios. Additionally, while IIT can explain how consciousness might emerge in systems like the brain, it does not fully address the nature of subjective experience, the hard problem of why these processes should feel the way they do. As we explore these theories and ponder the nature of consciousness, it is important to recognize that we are on the frontier of a vast and largely unexplored field. While neuroscience has made significant strides in mapping the brain and understanding how different regions of the brain are involved in various cognitive functions, we are still far from understanding how these physical processes give rise to the rich tapestry of subjective experience. The brain, with its intricate network of neurons, remains one of the most complex structures in the known universe, and consciousness, the product of its activity, may be even more mysterious. At its core, the study of consciousness is a search for meaning. We want to understand the nature of our own existence, the very essence of what it means to be. Consciousness is what makes us aware of ourselves, what allows us to reflect on our thoughts, our feelings, and our place in the universe. In a sense, it is consciousness that allows us to ask the questions we are asking now, to wonder about the origins of the universe, the nature of time, and the possibility of life beyond Earth. The search for consciousness, then, is not just a search for a scientific explanation but a search for something deeper, a quest to understand our own place in the cosmos and the very nature of existence itself. As we move forward in our exploration of the mind, we are bound to encounter even more questions, more mysteries. We may never fully unravel the enigma of consciousness, but it is this very mystery that drives us to explore further, to seek answers that may one day reveal the ultimate truths about the nature of reality and our place within it. Consciousness is not just a puzzle to be solved. It is the very lens through which we experience the universe, and it may be the key to unlocking the deepest secrets of existence. As we continue to probe the mysteries of the cosmos, one of the most confounding and awe-inspiring challenges remains the search for a unified theory that can explain everything in the universe, from the smallest particles to the grandest structures of space. This pursuit, which has occupied some of the greatest minds in physics, mathematics, and philosophy, is often referred to as the search for the theory of everything, TOE. At its heart, this quest seeks to answer a simple yet profound question: can all of the fundamental forces of nature be explained by a single, unified framework? In the end, will we be able to understand the workings of the universe in its entirety, in the same way that we understand the laws of physics that govern the motion of objects on Earth? The search for a TOE is, in many ways, the ultimate challenge in science. It represents the ambition to unify the entire fabric of reality under one coherent theory, to connect the disparate branches of physics, and to finally explain how everything in the universe, from the behavior of subatomic particles to the movement of galaxies, fits together in a single, grand narrative. It is a question that has preoccupied physicists for more than a century, beginning with the work of Albert Einstein and continuing to this day with cutting-edge research in quantum mechanics, string theory, and other areas of theoretical physics. To understand the significance of the search for a theory of everything, it is essential to first understand the two pillars of modern physics that have emerged over the last century: general relativity and quantum mechanics. These two theories form the foundation of our understanding of the universe, yet they are fundamentally incompatible with each other in many ways. General relativity, developed by Einstein in the early 20th century, describes the force of gravity and how it governs the motion of massive objects, from planets and stars to entire galaxies. It posits that gravity is the result of the warping of spacetime caused by mass and energy. According to general relativity, space and time are not separate entities but are part of a unified four-dimensional fabric that can be curved and distorted by the presence of mass and energy. On the other hand, quantum mechanics, developed in the early 1900s by physicists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, describes the behavior of particles at the smallest scales, from atoms to subatomic particles like electrons and quarks. Quantum mechanics is based on the idea that particles do not have definite positions or velocities until they are observed. Instead, they exist in a superposition of all possible states, and their behavior is governed by probabilities rather than certainties. This probabilistic nature of quantum mechanics has been confirmed through countless experiments and has led to technologies that have revolutionized our world, from semiconductors to lasers. While both general relativity and quantum mechanics have been extraordinarily successful in their respective domains, they are fundamentally incompatible in several key ways. For example, general relativity describes a smooth, continuous fabric of spacetime, while quantum mechanics operates on the premise that the very fabric of reality is discrete and made up of tiny, indivisible units. When scientists attempt to apply the principles of quantum mechanics to the fabric of spacetime itself, such as near a black hole or during the Big Bang, they encounter a major problem. The equations break down and the predictions become nonsensical. This conflict suggests that there is a deeper, more fundamental theory that is capable of reconciling the two. The search for such a unified theory has led to some of the most exciting and speculative ideas in modern physics. One of the most promising candidates is string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings of energy. These strings, according to the theory, can vibrate at different frequencies, and the different vibrational modes correspond to different particles. In this framework, particles like electrons and quarks are simply different manifestations of the same underlying entity, a vibrating string. String theory offers the tantalizing possibility of unifying all of the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces, into a single, coherent framework. One of the key features of string theory is that it requires the existence of additional dimensions of space, dimensions beyond the familiar three spatial dimensions and one-time dimension that we experience in our daily lives. In fact, string theory predicts that the universe has as many as 10 or 11 dimensions, though these extra dimensions are thought to be curled up and not directly observable. The extra dimensions are believed to be compactified, meaning they are incredibly small and hidden from view, but they play a crucial role in the interactions of the fundamental forces. This idea of additional dimensions is a striking departure from our classical understanding of space and time and raises the possibility of a much richer, more complex universe than we can currently perceive. Despite its elegance and mathematical beauty, string theory has not yet been experimentally verified. One of the major challenges in testing string theory is that the scales at which its effects would become noticeable are far beyond the reach of current technology. The energies required to probe the extra dimensions predicted by string theory are many orders of magnitude greater than what we can achieve with even the most powerful particle accelerators, such as the Large Hadron Collider. As a result, string theory remains largely a theoretical framework, one that is not yet subject to direct experimental validation. Another promising approach to the theory of everything comes from the field of quantum gravity, which seeks to reconcile general relativity with quantum mechanics. One of the leading candidates in this area is loop quantum gravity, which attempts to describe the fabric of spacetime as a network of discrete loops of quantum information. In this view, spacetime itself is quantized, and the smooth continuum of general relativity is replaced by a granular structure. Loop quantum gravity, like string theory, holds the promise of providing a unified description of the fundamental forces, but it too remains in the realm of theoretical physics, with limited experimental evidence to support its predictions. As we explore these theories, we are confronted with a deeper question. Is it even possible for a theory of everything to exist? Some scientists and philosophers argue that the very concept of a unified theory may be an illusion. Perhaps the universe is too complex and multifaceted to be captured by a single theory, no matter how elegant or comprehensive it may be. After all, the search for a unified theory has already revealed that our understanding of the universe is far more nuanced than we once thought. The universe is not merely a collection of particles interacting according to fixed laws. It is a dynamic, evolving system in which new phenomena emerge at different scales and in different contexts. Furthermore, the search for a theory of everything raises profound philosophical questions about the nature of science itself. What does it mean to understand the universe? Is science merely a tool for making predictions and observations, or does it strive to uncover the ultimate truths about reality? If we were to find a unified theory that explained everything, would that be the final step in our journey of understanding? Or would it open up new mysteries and questions that we had not yet considered? One thing is certain, the search for a theory of everything is not just a scientific endeavor, it is a quest that touches on the very essence of human curiosity and the desire to make sense of the world around us. It is a journey that transcends disciplines, from the intricacies of mathematics and physics to the realms of philosophy and metaphysics. Whether or not we will ever arrive at a unified theory remains uncertain, but the pursuit itself has already yielded profound insights into the nature of the universe. In this way, the search for a theory of everything is not just about finding answers, but about embracing the mysteries that lie at the heart of existence. It is a quest that continues to inspire, challenge, and propel us forward into the unknown reaches of the cosmos.